my report about correlation and regression using R. So now I'm going to report about how to make a correlation matrix using R. So I just input the data by copying all of this from the Word document that you just sent to us, and then paste it in the console editor, and then I save all the observations from our data into an input data. So I name it input data. Now we just need to run this command by placing it at the very bottom to input. So in my case, that line 107. So if I click it run, then you can see that the input data file has already been added in a global environment on the right side of the interface of the RStudio. We can actually import the CSV files that we just created using the code that I just showed you on my second part of the my report. So the next thing that we have to do is to input or to put this input file into a data set called data with capital letter D. It's up to you what file name would you like to do, what you like to choose. So this time we use the function read that table function. So this will read the data or the input file and save it into a data with capital letter D. So this will going to show us in a show all the information that we have in there into a tabular format. So sorry. So if I run this one, so as you can see that the data set data has already been added in our environment panel on the right side here. Now we have a code here. We have to order factors by the order in our data frame. Otherwise, the R will alphabetize them in order. So we can use this code over here to do that. And then after that, we have to install the site package using the install the packages function. I have already done that, so I don't need to do that. Then we need to access or load up the site package using the library function. Of course, I'm going to do that. And then this head and tail function will just going to show up the upper and the lower portions of the data set, my data sets. This is going to be helpful for a quick look of how our data look like. So if I run that one, you can see that the head is represented by the first 4 observations of our data set, and the tail is represented by the last 4 observations of our data sets. Now moving on is the str function over here. So this one is we can use this one to check what type of data do we have on our data sets. Just type in the str, and inside the parentheses is the name of the data sets or file that we have, and then click it run. Click it run again. All right, so as you can see, the instructor column is a factor type data, and the rest are in integers. So we have the grade, weight, calories, sodium, and score as integer. So the summary function will show us the show you. So the summary function will just going to show us the minimum and maximum values, as well as the first and third quartile values of each variable. So we have 6 variables in here, and it'll give us the minimum and the maximum values for each of the variables, as well as the first and quartile values for each of the variables of the variables that we have in there. So this is pretty much we have in here some useful information that we can check before we go on with our correlation correlation analysis. Now I want to remove the input file using the rm command or function, and then the paste function can plot multiple numeric or integer over here variables. So in a single plot to look for a correlation among the variables. So instead of looking on the numbers, so visualizing the scatter plot of the 5 integers can give us an easy interpretation about which variables are actually closely related to each other. And as you can see here on my command here, you can see that I have listed the 5 integer that I want to work with. 5 integer variables separated by plus sign. So why I excluded the instructor variable using the null function, because we don't need that, because we do need for the correlation analysis, since the this type of variables is the factor one. So we only need the integer variables in order for us to pursue the correlation analysis. I'm not going to run for this one, but because I've already done that, explaining it in the first part of my video, sorry, in the second part of the video. But I'm just going to run that one for us to do it. Now, since we don't need the first column in our data set to be included in our correlation analysis, this is the name of the instructors, as we have said earlier. So we need to create a new data frame. Let us name it data.num. And then put all the class integer or numeric type variables within it. So all these variables in it are integers, and we're gonna have to put that in a data.num variable. So let's run this one. So then what we need to do next is to load up the site package again. So if you haven't installed this package yet, you may use the installed packages function. Okay, so let's run this one. And we can now proceed to the correlation test to have a look at the correlation matrix. Now, let's use this Quartis function to measure the relationship among the variables. This correlation test will actually give us an output in terms of matrix. So I have already run that. But as you can see at the terminal window, that it actually gives us the correlation matrix values result. So let's have a look in this Codeplot here, and upon visually inspecting each of this Codeplot, I can see that the white and calories have some sort of strong correlation. Now, let's go back to the correlation matrix. And as you can see here, these numbers are just the values of R coefficient, or the correlation coefficient, and each of the scatter plots over here. So as you can see, the correlation of 0.99 for white in calories, and that indicates a very strong correlation between these two variables. Similar to that, when we inspect with the scatter plots over here, as you can see, the white in calories have a strong correlation, which is indicated by a very steep, straight line that is looks like going up. All right, so looking at the bottom of the result of the core test, or the correlation test, it's actually telling us if we want to see the confidence intervals within the correlation or the correlation matrix. So we shall print the short to false options. So now we can actually save or create a data frame for a correlation matrix. So in our example, we call it core matrix. Then followed by these two signs over here. Then we specify the Quartis function for the dataset's data. So this is the Quartis, and then this one, and then we specify the type of the correlation analysis that we want to use. In our example, we use the person correlation analysis. So let's run this one. And so the console here will tell us that the core matrix has been successfully created. So as you can see it here on a global environment here, that the core matrix has been added on our current workspace. So we can print the whole core matrix, but this time by setting the short to false. So let's click this run. And as you can see, at the bottom of the correlation matrix, or the bottom of the core matrix is has now a value for the confidence intervals. So here, the confidence interval for grade versus white, grade calories, grade versus sodium, and so on and so forth. We can export this core matrix into a CSV file format. So let's say we want to export the correlation coefficient for core matrix. So I use the write.csv function over here, and within the parentheses is the name of the data frame, core matrix, which is the core matrix, so followed by the $, and then small letter R. This means correlation matrix for persons correlation is being used. And then within the double quote in green is the name of the CSV formatted file. So do not forget to write the .csv at the end of the file. This file extension will help us work flawlessly across the Excel or R. So you can use whatever name you want in here. The default here are actually this one and the $, and R. Now let's say we want to export the correlation matrix that contains the p-value. So we can just change this small letter R into small letter p, and of course we must choose a different file name. Okay, so same procedure goes when we want to export the correlation matrix that contains the confidence intervals. So we can actually type in, replace with R or P with small letters C and I, and then of course we choose different file name for that. So when we run all these three here, you should see that the save files within your current working directory. Now, I'm not going to run this three because I have already done it, so let's move on. Now, if we have a look closely on our core matrix, again over here, the upper and the lower data on the table are just replicates. So it's pretty much confusing. So for us to show that the lower portion of the correlation matrix, we can use the lower core function. So do not forget to specify the method here. So we use the person's correlation analysis, and then we run this one. Okay. Run this one. And as you can see, it just printed the lower portion of the core matrix dataset, which is way better to interpret, of course, than the numbers, because the other numbers on top of it are just replicates of the bottom numbers. Okay, so by looking at the correlation matrix where we have confidence interval displayed at the bottom of the other correlation matrix, we can actually create a more professional looking correlation matrix, which is easier than very easy to visualize and understand using the Apache Tables package. So first is we have to install the Apache Table package and access that in our library. I have already installed the Apache Table, so I need to access that with my with the library function, and then we use the function apa.core.table, and within the parentheses we write in the data. Now the output will give us numbers with a designated number of asterisks on top of it. So let's run this one first to have a look at what this looks like. Sorry. Let's try the one. So now the output will give us numbers with designated number of asterisks, as I've said earlier. The asterisk on top right of each number, just like this, and the two numbers at the bottom within the bracket. So the three asterisks, so since we don't have three asterisk sims here, okay, since we don't have three asterisks, I'm just going to say it. The three asterisks means that the number is significant at 0.001, or p-value is less than 0.001. Now we have these two asterisks here, meaning that the correlation coefficient between the white and calories, or the grade in calories rather, is significant at 0.02 because it has two asterisks. This means that the p-value is less than 0.01. Okay, so one asterisk means significant, that the number is significant at 0.05, or the p-value is less than 0.05. And finally, if we don't see any asterisks over here, that means that the number is non-significant. So those two numbers inside the brackets are the numbers at a confidence, 95% confidence intervals. So we can actually export that in Word document. Just use the function apa.core.table, and within the parentheses are the name of the data and the name of the file that you want to save using the doc file extension. Again, I will not run this one, but once you did, you should be able to see a Word document in your current working directory. Now, there is another way to visualize this trace correlation matrix into one. So, in its Codeplot, that's what I mean. So the correlation matrix into one, showing Codeplot, an histogram, and at the same time the numerical value for its correlation coefficient. So first, we need to create a data frame called data.num. So this one contains only the numeric and integer variables. So in our problem, these are the grade, the weight, calories, sodium, and the score. And I know we have already done this earlier, but it is more important to do it again, especially when we have loaded a few packages from our library. So let me do that. Okay, so executing the lines from 167 to 170 will actually give us an assurance the variables that we are trying to work into are within the appropriate class. Okay, to visualize Codeplot, histogram, correlation coefficient, and significant level into one correlation matrix, we need to install the package called Performance Analytics. So I have already installed it. We have to just access it from our library. And once you've done that, we can use the chart that correlation function, and then within the parentheses we can specify the data frame we want to work with. In our case, this is the data.num data frame. Then specify the method that we want to use, so which is person correlation for our person's correlation analysis. We also want, if you want to use the Kendall or Spearman for this method, we can just like replace it with a word Kendall or Spearman. And then we set up the histogram to true because we want to show, we want to include the histogram in our correlation analysis matrix. So we can see that. The distribution of data within the data sets, and then we can actually set this PCH equivalent to 16. This is just a type of the PCH argument in A. So 16 is a shaded circle. So you can change that to a certain value and see how the data points basically changes in shape. So now let's run this one. Okay, as you can see on our scatter plot panel here, you can see the distribution of the data across the calories and weight variables in these two histograms over here are pretty much the same, with a red, a belt-shaped red um, line in here. For calories and weight, they're pretty much the same. That means the distribution of data for these two variables are pretty much the same. The bottom portion of the correlation matrix shows this scatter plot over here, and from there, weight and calories again seems correlated to each other. As we can see that this one, the data seems the data points for weight and calories seems following the straight line, which indicates that the correlation between these two variables is pretty much strong. Okay, moving on is at the upper portion of the matrix is the value of the coefficient, our correlation coefficient. Again, we can see the value for the correlation coefficient for weight and calories is 0.099 and 0.99. That's very close to 1, which is, of course, suggests a strong correlation. The correlation coefficient of 0.99 is significant at 0.001. This is represented by the free asterisk on top of it. Also, as you can see, the variable score has the weakest relationship among other variables. You can tell that by looking at this number over here. It's 45. T is the lowest calculated correlation coefficient among all the variables. So if you want to export a scatter plot like this, let's say we want to save this one, we can use actually the export icon here. So we just like to click that one, and then either we save it as PDF or save it as an image. So this actually how to visualize the correlation matrix using so thank you for listening.